Okay, so today we're going to look at the fascinating theory of imaginary points and imaginary lines in geometry. Now, imaginary elements have invaded the theory of algebra quite significantly, with the idea of an imaginary number as the square root of a negative number, the thing which, if you times it by itself, gives a negative number. And our theory of geometry is completely consistent with this, but we're going to look at these imaginary elements from a purely geometric view. And this is very interesting because although we can't see these elements directly, what we're going to learn is that they do have a remarkable influence on geometry. So, for example, if we look at these two circles, if we move them like this, so they're close to each other, we can ask, where do these two circles meet? And quite clearly they meet at these two red points here. But what happens if we move one circle away from the other? We see these two contact points merge, and then they seem to vanish. Where do these two circles meet now? Well, they certainly don't have any real points in common, but in fact, what we'll see is that they do, in a sense, still meet. It's just that now their common points are imaginary. And this is not at all a nebulous concept. It can be studied in complete detail using geometric elements we can visualize. Okay, so our road to understanding these imaginary points and lines in geometry is going to involve looking at a mapping from the points on a line to itself. We're going to look at a special kind of mapping which is induced by a conic, in this example a circle. So to begin with, we put 3 points on the circle, A, O and O'. The origins of projection, O and O', are going to define how our mapping works, and A is going to be the starting point of our mapping. So how does it work? Well, we have this black horizontal line here, which we shall call M. And what we're going to do is, we'll start by drawing an orange line between A and O. And we're going to look at where that line meets with the black line M. We'll call that point A'. Now what we're going to do is project A' back onto the circle again, using the other origin of projection O'. So we draw a line between A and O' and see where it meets the conic for the second time. We'll call that point B. And what's happened on our mapping is, using O and O', we've mapped A to B. So, as well as being a mapping from a line to itself, this is also a mapping from a circle to itself. And it maps the circle point A to the circle point B. And we shall repeat the process here. And so we draw a line from B to O, and then see where that meets the black line at B', and then joining back from O' to B', we get a point C on the circle. And we can repeat this kind of iterated projection procedure. Now what's happened here is that we have a mapping from the points on the circle to themselves, but we also have a mapping from the points on the line to itself, to the points on the line. And it turns out that those points have a very special relationship with each other. But let's just have a look at the sort of qualitative aspects of this kind of mapping. Firstly, we can see that there are going to be two fixed points on the mapping, the points where this line meets our conic. And the point on the left here is attractive, and the point on the right is repulsive. So we have an attractive fixed point and a repulsive fixed point. Also note that by moving around these origins of the projection, we can change the qualitative nature of the mapping. Now the right point is attractive and the left point is repulsive. So using this kind of dynamic, which here is called growth measure, we can understand quite a lot about the fundamental connections between projective geometry and arithmetic. Okay, so projective geometry is more general than Euclidean geometry because its truths don't rely upon measurements. We're just using straight lines and thinking about general conics and so forth. However, let's just for a second restrict our attention to the Euclidean plane and see if we can get an understanding of the metric relationship between these points A', B', C', and so forth, which this process makes upon this black line. Well, to do this, let's call the left contact point of the black line with the circle X, and we're going to draw a line through X and a parallel line through the other contact point of the circle and the line. And we're going to pick a point on that second line, this blue point here, and we're going to project A', B', C' and D' onto the other line. So that will look something like this. We'll call the projection of A', A double dash, and so forth. Now, it's interesting to ask, what's the difference between the measurements of these points A', B', C' and D' from this point X, which they're sort of exuding from? So let's do some measuring. In this setup, the distance from X to A double dash is 0.53, A to B double dash is 0.89, X to C double dash 1.49, and X to D double dash 2.49. So how are these numbers related? Well, let's just do some simple calculations. So if we take 0.89 divided by 0.53, we get 1.67. Now let's divide the next two numbers, so 1.49 divided by 0.89, we get the same number, except there's a rounding error. And similarly, 2.49 divided by 1.49, again the same number. So we have this very interesting thing that to get the next point on the sequence, we find out how far away the current point is from X, and then we multiply it by a given sort of constant ratio. When the line doesn't meet the circle anymore, it's again quite profitable to ask, what are the fixed points of the system? So when the line did meet the circle, the fixed points are the places where the line intersects with the circle. And then shifting the line up, we could say, well, now there are no real fixed points. These points on the line, they're always getting mapped to the right in this case. by smaller and smaller amounts as we get closer to the place where the line is nearest to the circle, but they never stop. So we could say there are no fixed points, but it would be more precise to say that there are no real fixed points. And in fact, what we can say is that the fixed points of a system are imaginary points of this line, which are identical to the place where this line meets this circle. So of course the line doesn't meet the circle at any real points, but if we think of a more general view of the system, we could say that the line does meet the circle at imaginary points, just the same as if you try to algebraically solve this system to find where the circle defined by the equation x squared plus y squared equals 1 would meet a line defined by the equation mx plus c equals y. Sometimes if the line goes through the circle, the common solutions of those two equations will give you real points, of course, but when it doesn't, that equation will give you imaginary solutions, and we can find those just the same imaginary solutions geometrically. But what we're going to have to do is take another sort of view of this process, which is just the same as before in its definition with respect to lines through O and O dash. It's just that now the line doesn't meet the circle. So we get a sort of dynamic or sequence, and the only thing that's really important here is how this sequence works upon a particular point on the line. So you see I've drawn this green arrow here showing how A dash maps to B, and by moving A dash around we can see how all the different points on the line are translated to the right. And what we're going to do now is look at this translation in a different sort of way. We're going to see that it's actually related in some way to thinking about how a watch on a table is going to point at different places on a wall. So now we're going to have a look at a more concrete view of this circling measure. And so again we're going to throw in some Euclidean concepts to help with the definitions, although there are ways to look at these things in more general terms. So the basic idea of this kind of primary view of circling measure is that if we have a point, say this dark blue point here, above a line, well firstly let's just think about what happens to the lines of this point. And the kind of motion we're going to imagine is just one of rotation. So any line, let's say this one here, is going to be rotated by a fixed angle, centered upon, and the rotation is centered upon this blue point here. So in this case we have a rotation of 72 degrees, which makes this line go to this line, and so forth. We generate this whole sequence. And so what we then think of is if we just project this kind of motion onto a line, this black line here, by looking at the different places where these red points, these red lines, intersect with this black line. And so what that does is project this kind of circular motion onto the black line. And then we can think about what the dynamics are like. So basically every point on this black line is mapped to another point which corresponds to 72 degree rotation about this sort of centre of rotation above. Now this is one particular setup of circling measure. Again we say that this system doesn't have any real fixed points on the line, but it does have imaginary fixed points. Now what we were looking at before with the growth measure was that there was a couple of real fixed points, and those fixed points were common irrespective of the kind of motion that was induced, as in irrespective of the positions of those two green points O and O' in our previous diagram. And what we've got here is something a bit similar. Here we've decided to do motion which involves 72-degree rotations, but we could have chosen to rotate by 5 degrees, or 2 times the square root of 2 degrees, whatever. The point is that whatever we do, clockwise or anti-clockwise rotation or whatever, we're going to induce a certain mapping of this line to itself. And we're not specifically interested in how many degrees we're mapping it, because all of these processes, provided they're all about the same kind of central point, as in provided this dark blue point doesn't move, the imaginary fixed points of this motion are always going to be the same. So they don't depend on the specific angle, they just depend on the relative positions of the centre of rotation and the line that we're doing a rotation of we're doing the motion of points on. So then what are these fixed points of this line? Well, the way we work it out is, if we have a look at some 45-degree angles, firstly let's drop a perpendicular from this point. Now we can look at these 45-degree angles. And now if we mark these on the line, where these 45-degree angles from our centre of rotation meet a line, these actually give us the imaginary part of our fixed point. Okay, so once we've got our centre of rotation, we can drop this 90-degree angle from the centre to the line that our motion's occurring on. And then if we want to find the imaginary fixed points, or perhaps it would be more precise to say complex fixed points, as a complex number has a real and an imaginary part, so a complex fixed point has a real and imaginary component. Well, to find the complex fixed points of this motion, we know that these fixed points, they have the form we can think of them as numbers, because we can think of the points on this line as numbers, and so we can think of them as having the form a plus b times the square root of minus 1 and a minus b times the square root of minus 1, where a and b are real numbers, or lengths if you like. And so a is the real component and b is the imaginary component. How do we find them? Well, we find the real component of the fixed point just by dropping a perpendicular from our centre C of rotation onto our line. And then if we also drop 45-degree angles, now this is a metric notion of course, but it turns out that these things can be defined purely in projective terms. But anyway, if we drop these 45-degree angles and we find where they hit the line, and then we measure these two intervals from this sort of middle point, which gives the real part of our complex fixed point, well, the size of each of these two intervals will be the same, and it will be equal to b, and we can call b the imaginary component of these complex fixed points. So we have two of them, one at a plus b times the square root of minus 1, and one at a minus b times the square root of minus 1. Now, it's not true that the fixed points of this system are here and here. That's obvious, because if we rotate our point around, the motion of it never stops, so it doesn't have any real fixed points. What this method does is it gives us a way to measure the amplitudes of the complex fixed points of this system. It doesn't show us the imaginary points of the system directly. We can't see them because they're not real, but we can measure them in this way. Now, I'll go on later to give a better interpretation of this perhaps, but let's just take a look at something else. How can we think about this? Well, let's move our center of rotation much closer to the line and look at the dynamics again. So now our imaginary point has got smaller, and if we look at our motion, we see that it does get closer to having a fixed point, a real fixed point, because the motion gets slower and slower. Of course, it gets slower and slower as the point we're mapping on the line is close to this real part A of these complex fixed points. But obviously the motion never stops, and we can think of that as a consequence of the fact that these complex fixed points do have a non-zero imaginary component. Now, were we to move this point all the way down to the line, the imaginary component would vanish, and indeed at that point this motion would have a real fixed point. Similarly, if we move the centre of rotation far away, again the slowest place is at this real part of the complex fixed point A, but now since the amplitude B is massive, the motion hardly slows down there, because it's always moving, because the complex part of this fixed point has rather a large size. Okay then, so a question then is, how does this circling measure, as induced by a point of rotation, correspond with the circling measure I was talking about before, when we do our kind of O and O' based bouncing lines projection of a line that doesn't intersect with a conic? I said those are both called circling measure dynamics. So how do they correspond with each other? Well, does the previous dynamics also correspond to the rotation about some point? Well, it turns out that it does, but that's finding that point is often quite involved, and it's best to think of these sort of dynamics as something which you can project and still get the same type of dynamics. So to illustrate this, what I've done here is I've put an extra blue point on and an extra purple line, and then I've projected the dynamics on this upper black line onto the dynamics on this purple line. So these were initially induced by this rotating blue point at the top here, but now, I'll just get rid of those, they're confusing, but now we're projecting it onto this purple line. So clearly this purple line is not going to be the sort of centre of rotation which induces this movement of points on the purple line. But there is going to be such a centre of rotation. It's just a matter of finding it. And this is also true of the dynamics on the circle, which we looked at before. We can find a particular place where their motion corresponds to a rotation about a point. So those dynamics are also circling measure dynamics. Okay, so what I'm saying here is that these dynamics induced by this conic onto this line that doesn't meet this conic in any real points, excuse me, that these dynamics, it is a circling measure dynamic, and as such it has imaginary points. But if we're going to work out what those imaginary points are, then it's going to help to be able to find where the centre of rotation is, which induces these dynamics. So in other words, there's a place in this picture, there's a point such that the angle at that point between A and B dash is the same as the angle between B and C dash, and the same as the angle between C and D dash, etc. Where is that point? Where is the centre of this rotation? If we can find that out, we can drop our 45-degree angles and perpendicular, and we can calculate the values of this complex fixed point of this motion. Excuse me about saying imaginary fixed points repeatedly. It's the term used in the literature. I'm just trying to correct my habit because I don't think it's precise enough. Anyway, let's see if we can do this. So an alternative way to think of this, these fixed points of this motion are they're the meeting points of this circle and this line. So how do we work them out? Well, firstly let's get rid of all of this gubbins. It won't really help us. I'll leave these points on the line just. We're going to use them later. So if we get back the centre of our circle, and we'll drop a perpendicular for it to the line. Find where it intersects the line. So I'm not going to explain why this construction method works here, but I'll sort of try and demonstrate to you that it does. So if we draw tangents, I mean this point here that I've just put down, it's not called C dash, it's confusing. This point that I've just put down, that's going to be the real part of this complex fixed point. Now I draw tangents from it, and also I'll draw perpendiculars to it where it meets the circle. Now if we join these points, that gives us two positions on the line, here and here. And now it turns out that the imaginary component is given, the amplitude in other words, is given by the interval in between these intervals in between these points, just as before. So I'll use cerulean blue again to represent this. So just to sort of demonstrate that this works, so what I'm saying here is that if we have this distance here between this central point and say this left, between this middle point and this left point, if that's B, and we call the position of this point little a, and this is little b, this distance here, then the complex points where this circle meets this line have the form a plus the square root of minus 1 times b and a minus the square root of 1 times b. Perhaps a clearer way to think of it, if we look at angles, so if we draw these two 45-degree lines from each of this, then this point here that we just found, this is going to be the centre of rotation, which is going to generate this these circling measure dynamics. So I said there was a certain centre of rotation, just as in my last picture. So if all has been done correctly, and we draw these lines from here, we should find that the angles between these points are the same in each case. Between these lines are the same. Okay, we want to measure angle the other way around. 0.07 degrees. Sorry, 10.707 degrees, 10.07 degrees, and 10.07 degrees. So using this construction, we've determined the amplitude of this imaginary point where this line meets this circle, and by drawing these 45-degree lines to where the amplitudes go out to, the amplitude representations, I mean these are just representations of imaginary things, but drawing 45-degree lines out, we get the actual place, the actual centre, which generates this motion. So rotation about this centre corresponds to these kind of bouncing dynamics that we originally induced using those points O and O dash. And this centre of rotation is the same irrespective of how those dynamics are induced in terms of the positions of O and O dash in that second picture which we looked at before. Okay then, so we can also see these imaginary points by thinking about this algebraically. So let's use Cartesian coordinates for a second, and if this origin is 0, 0, and let's say this circle is the unit circle, so it has the equation x squared plus y squared equals 1, and let's say that this distance here is h. So then this line right here, this line has the equation that y equals h. Okay, and so then we can ask, where are these two equations solve true at the same time? In other words, what are the horizontal values x where this circle meets this line? And so what we'd find is that y is equal to the square root of, we'd find that x, of course y would have to equal h, and x would have to equal the square root of 1 minus h squared. Now, when h is bigger than 1, of course the thing in this square root is going to be negative, and so what we're going to have is that x is going to be imaginary. Okay then, so let's return to our original question. Where do two circles meet? In particular, where do they meet if they're far away from each other? How can two circles that don't look like they meet actually meet at imaginary points, and what does this mean? Well, through contemplating this, we're going to sort of validate our old ideas that we were just looking at and see that they do actually have some teeth. So let's look at things that we know about ordinary circles. There are two sort of famous, well, quite famous Euclidean theorems. One is that if we have two overlapping circles and we draw the common chord they have, it's going to be perpendicular to the line in between their centres. Another theorem, which maybe not so quite well known, is that if we have three circles and we draw the common that mutually overlap, and we draw the common chords between each pair of them, they always meet at a point. It's actually a very important result for us, because what we're going to do now is suppose that those two results hold whenever there are two or three circles. So I'll show you what I mean. Let's suppose we have these two circles. Let's move this one across if I can. Oh, whatever, I'll just draw another one. Okay, so there's another circle. Where do these two circles meet? Well, to find this out, let's draw a third circle. And we'll colour this one purple to show that it's a piece of construction. And it should be big enough so that it goes through both of the other circles. Now, if there is a common chord between this left and right circle, supposing those Euclidean theorems work, it should be perpendicular to this line here, which goes through both. Now also, the three common chords between these three circles ought to be coincident. So let's draw in this common chord here. Just make sure I've got that right. And this one for here. So we'll draw in these common chords. And now, if there is a common chord between the left and right circle, our first fact means it should be perpendicular to this line, and our second fact means it should go through the meeting point of these two lines. So if we draw it in, it should look like that. So that is in fact the common chord of the left and right circle, and the meeting point between them has real parts like this green point here. So if this is true, then it should be that this line, which, I mean, what this line does essentially is it goes through, well, it has imaginary points in common with both of the circles at the same time. Okay, so let's just take a quick look at this picture again. Now, I'd like to suggest a rather radical new way of thinking of conics like the circle. Instead of thinking them as curves like x squared plus y squared equals 1, think of them as the set of all circling and growth measures which they induce. So, for a given position of a circle and a line, we can position these points O and O' differently, and they're going to induce different dynamics. And when I say dynamics, I mean all the different ways all of the points on this line can move to this line, which depends on where you start from. So that's one type of dynamics. And then there's a whole set of dynamics which can exist for different positions of O and O'. And so we can call that a dynamic collection. Now, what we can think of a circle as is the set of all dynamic collections there are as we move this point around. So when the line goes through the circle, we have a dynamic collection corresponding to growth measure, different kinds of growth measure. When it's outside, it corresponds to different kinds of circling measure. And so, in this sense, if we go back to our picture, if this black dotted line here, or grey, or whatever it is, this one here, if this truly is the common line, or the line through the common points of this circle and this circle, then, and what I said was true, it should have the same kind of dynamics induced upon it by both of these circles. Or at least it should be possible to induce the same kind of dynamics. So let's see if that's true. We'll put a couple of points like O and O' on the circle, and we'll have a starting point for our dynamics, and then we'll do what we did before. Okay, let me colour this real component of the meeting point cerulean blue. It doesn't get confused. Anyway, so we do this back and forth bouncy line thing just as before to get a sequence of points on this line which are induced by the left circle. Now let's see if we can get the same thing by the right circle. So we've got to pick our points like O and O dash on here carefully. So we'll just choose one to start with. We draw the line through here. And now what we want to do, if we just zoom in, we want to find the right place to put the other point. So if we project that back, it'll be there. So let's colour this lime green as well. Zoom out again. Right then. Now hopefully, yes, you see if we map back here, so we continue this generation process now using these two lime green points on this right hand circle. So we draw an orange line back to here and then we use this. You see we generate the same point again. So the fact that this orange line also goes through this green point is not, it's not mechanically determined, it's sort of causally determined, if you like. Okay, that's not a very precise way of saying it. What I'm saying is that there's no reason for this to happen except for that this line sort of represents the line through the common points of both of these circles, and therefore it's possible to induce the same kind of circling measure dynamics on this line using either circle.